Today we are doing section 5.2. We are going to simplify quotients of monomials and find the GCF of monomials again. So for starters, we're going to write the prime factorization of 42 and 56. So I'm going to make a little space down here so that I can do that. We'll bring those back in just a minute. When we are trying to find prime factorization, we start off by making a factor tree. Who can tell me what 42 breaks into? Kian? 2 and 21 works. And then we leave 2 alone because it is prime, but 21 is not. Who can tell me what 21 can break into? Natalie?
3 and 7.
3 and 7. Can we break down 3 anymore? What about 7? No. What number do we never use on a factor tree? The number 1. Okay, so the only things that 2, 3, and 7 could break into involve a 1. So we don't break those down anymore. We're ready to write our prime factorization. That would be 2 times 3 times 7. We move on to 56. Who can tell me what 56 breaks into? May?
2 and 28.
2 and 28 works for me. 2 is prime, 28 is not. Who can tell me what 28 would break into? Ryan? 7 and 4 will work. 7 is prime, 4 is not. 4 breaks into 2 and 2. So when we write the prime factorization for 56, we can either write it as 2 times 2 times 2 times 7, or we could write it as 2 cubed times 7. Either of those would work. Remember that if we break a number down, we don't use it in our prime factorization. So if you want to cross those numbers off as you break them down, you can. So that you remember they do not go on your list. Questions about those before I erase them to bring back our other problems? Okay. Let's take that all away so that we can do number 3. Number 3 says to find the GCF of 42 and 56. Now, luckily, we just did our prime factorizations of those. We had 2 times 3 times 7 and 2 times 2 times 2 times 7. When we're looking for the GCF, we're looking for matches of numbers from those lists. Who can tell me one number that matches on those lists? I need somebody new to raise their hand. Jamal Dixon. 2 is a match. So when I do that, I write down 1, 2. What else is a match? Lexi? 7 is a match. So I would write down times 7. Any other matches? Nope. The only thing that we've got left here is a 3. There are no 3s on this list, so we are out of matches. 2 times 7 is 14. That is our GCF. All right. Let's look at questions 4 and 5. Number 4 asks for the positive factors of 48. Number 5 asks for the positive divisors of 48. Does anybody know what's a little interesting about those questions? Ryan? It's the same thing. If you're looking for factors, you're looking for the divisors. Things that multiply to equal 48 are also going to be the same things that divide into 48. Does that make sense? So 4 and 5 are essentially looking for the same numbers, same list. So let's just make that list one time. When we did the positive factors or positive divisors, we did not make a factor tree. What did we do instead? I always started with which number? 1, and I paired it up with 48. 1 times 48. That means they're factors, a factor pair. That means they both divide into 48. After 1, I went to 2. 2 will divide into 48, so 2 times 24 is another factor pair. Will 3 divide into 48? Yes, 3 times 16 is a factor pair. Next, we check 4. Should 4 go on my list? What's its pair? 4 times 12. Should 5 go on my list? No, it should not. What about 6? 6 times 8. All right, what about 7? No. Do I keep going? Why not? Good. If we count up again, we go to 8. 8's already on the list. So we're just going to start repeating ourselves. That's how we know our list is complete. Questions, concerns? Ready to continue? Okay. All right, first we've got the property of quotients. If A, B, and D are real numbers with B not equal to 0 and D not equal to 0, then AC over BD equals A over B times C over D. Really, this is like a multiplication fraction problem written backwards. Okay? We could break this apart into 2 fractions that were multiplied together because we know that multiplying fractions means we go straight across the top, straight across the bottom. So we could rewrite a division problem separated. This should not be mind-blowing. Are we okay with this property? It should be somewhat familiar. Are we ready to practice this a little bit? Okay. So when it says to simplify each quotient, now some of you are great at reducing fractions already. So you might be able to look at 15 over 21 and be able to go straight to your answer. We are going to write 15 out as its prime factorization. What 2 numbers would multiply to 15 that does not involve a 1? 3 and 5. So 3 times 5 is the prime factorization of 15. And then 21, its prime factorization would be 3 times 7. So what that property on the last slide was saying is that we could rewrite this as 3 over 3 times 5 over 7. And we know that 3 over 3 reduces to be a 1, a big old 1. And 1 times 5/7 is Anybody? 5/7. Now, on a quiz or test, if you were asked to simplify 15 over 21, I do not expect you to show all these steps. These steps are just illustrating that property we just talked about. That you can break a number apart into a product, a multiplication problem, and then you're able to split it up to simplify. Most of you learned a long time ago to do that much more quickly, but this is how we would illustrate that property. All right, let's see if we can do something similar on number 2. Now, if we think about 20, and we want to do its prime factorization, what would it break into? 5 and 4. 4 can break into 2 and 2. So let's just rewrite it with a prime factorization. 2 times 2 times 5. Let's also do a prime factorization for 48. 48 can break into what? I think I heard 4 and 12. There are other options. Let's just stick with 1. All right, and then 4 breaks into 2 and 2. 12 breaks into 2 and 6. 6 breaks into 2 and 3. So now, how many 2's do we have? 4 of them, and a 3 on the end. So we're not going to necessarily split it up this way, but now what can I cancel out? Pair of 2's here. What else? Another pair of 2's. So I'm left with what on top? 5. And in the denominator, what do you think I'm going to do with those numbers? Multiply them back together and we get 12. So that's using the same property that we used before. We just showed it in a few less steps. Again, I don't expect you to do this every time you have to simplify a fraction if it's just numbers. But this idea might help us when we don't just have numbers, we also have variables. All right. Ready to move on? I know this hasn't been terribly exciting yet today. It gets more exciting when we start throwing variables in there. Okay, another property that we already talked about a little bit. If B, C, and D are real numbers with B not equal to 0 and D not equal to 0, then BC over BD is equal to C over D. What did they do to get from the left side to the right side? What canceled out? The B's, right? B over B would equal 1. It's the same kind of thing that we saw on the last problems. Now, they keep on saying on these things like B and D not equal to 0. Does anybody know why they have to say that? Seems extra, but they have to say it because where are B and D located? In the bottom, in the denominator. Can you have 0 in the bottom of a fraction? No. Okay, so if you keep on wondering why they keep repeating that, it's because they cannot have 0 in a denominator. Let's simplify these as well. What factor are 35 and 42 going to have in common? What can both of them be divided by? Do we need to make our prime factorization? What am I going to break 35 into? 5 times 7. What about 42? 6 times 7. Now, 6 is not prime, but I'm going to just leave it as a 6 for now. What's going to cancel this time? The 7s. So that's the factor that they both have in common. And what are we left with? 5 over 6. All right, on number 4. What's a little different about 4 from what we've seen so far? Natalie? It has variables. What else? Jamal? It's got a negative. Okay, these are things that we have not dealt with yesterday or today, variables and negatives. So if I'm going to rewrite -4 into factors, what do I have to rewrite it as? It's not a trick question. If this was a 4, what would I rewrite it as? What times what? Okay, we would write 4 as 2 times 2, but if it's a -4, we need one of those 2's to be negative. What's the exponent on this x? A 1, and on the y? A 1. So I'm just going to write 1x and 1y. In the denominator, 10 is going to break into 2 times 5. And how many x's do we have? 1x. What's going to cancel out? The x's will cancel. What else? The positive 2's. What does that leave us with in the numerator? -2y over a 5. Okay, so if we expand everything out, we can see what cancels so that we're able to write what's left. All right. The next rules are ones that we've technically seen. We've talked about what to do when we divide the same base. If you divide the same base, what do we do with our exponents? One person whispered it. You subtract them. Okay, that's what this slide is saying. So in your notes, in that box, you got to fill in that right side. A to the m divided by a to the n is equal to a to the m minus n. And up at the top of this, it says if m is, what's that symbol mean? Greater than n. If m is bigger than n, then when you subtract them, you will get a positive number, right? If m is bigger than n and you subtract, you get a positive. Like if this were to be a 3 and a 2, you'd end up with a positive 1. Does that make sense? Okay, it's different on that next step down. Now we're talking about if n is bigger. So if the number in the bottom is bigger and you were to subtract m minus n, you'd end up with a negative. So they're going to reverse it. If the number in the bottom is bigger, they're going to do bottom minus top, but then it has to live in the denominator. So this is something we haven't quite seen. We didn't really deal with this scenario when we were doing our exponent rules. Okay, the last rule or last scenario is if m and n are the same number. If m and n are the same and you subtract them, what would you get? 0. And anything raised to the 0 power is equal to 1. So that's why if your exponents are exactly the same, top and bottom, with the same base, it'll just come out to be a 1. They'll cancel each other out completely. Let's practice simplifying then. Is our bigger exponent in the top or the bottom? The top. So are we going to need to write this as a fraction or not? No. If your bigger exponent's in the top, it does not need to become a fraction. So we're just going to take what minus what? 7 minus 4, and we end up with a to the 3rd power, a cubed. If your bigger exponent is in the top, you just subtract and leave it alone. Do not worry about it being a fraction. Ready for the next one? Number 6. Now where is our bigger exponent? In the bottom. So if our bigger exponent's in the bottom, we need to turn this into a fraction with what on the numerator? A 1. And in the denominator, what order are we going to subtract in? What minus what? 8 minus 3. Big number minus little number. So it's still going to be 1 over, when we take 8 minus 3 we get 5. So we have x to the 5th. And we're done. Positive exponents only. Questions about 6? Okay. On number 7. Number 7's a little bit different because we have some rules we have to apply before we start worrying about subtracting our exponents. Anything inside parentheses gets the exponent that's outside of it. We remember that rule? Anything inside gets the exponent that's outside. So we have to give that exponent to both the x and the y. If I'm not sure what to do about this negative sign out in front, what number could I turn that into? A -1. So if you're not sure about that negative sign, turn that into a -1. Is it going to get that 9? No, why not? It's not in the parentheses. So the -1 just hanging out in front. We have x to the 9th, y to the 9th. Over, does this x in the denominator get a 9? No, it does not have parentheses. That 9 only belongs to the y in the bottom. If I wanted to write an exponent on that x, what would it be? A 1. Y to the 9th. All right, if it makes you feel better to initially write a fraction bar, you can. You don't have to. We know that this -1 is still just going to hang out in front for now. Nothing going on with that. If we're looking just at our x's, do we have a bigger exponent in the top or in the bottom? Bigger exponent's in the top, which means that the x is going to stay in the top. We don't have to worry about moving the x down into a denominator. So we would take x to the 8th. 9 minus 1 gives us x to the 8th. Okay, really the end story here is that wherever your exponent started out being bigger, that's where that variable will end up. If you have a bigger exponent in the denominator, that variable in the final answer will live in the denominator. If you have a bigger exponent in the numerator, that's where your variable will live in the end. For the y's, what happens? They cancel each other out because their exponents are the same. They're both 9s. 9 minus 9 would give us a 0. Anything to the 0 power is 1. So if you want, you can put a times 1 on the end. In the very end, we would just end up with negative x to the 8th. -1 times a positive 1 is still a -1. If you want to write the 1 in front of the x, you can. You won't normally see it there, though. Questions about our exponent rules? Okay. We're almost to the stuff that I find a little more interesting. When finding the GCF of two monomials, you must circle both your number matches and your variable matches. Circle both your number matches and your variable matches. Okay, so we're going to work on finding the GCF of these two monomials. So we're going to still write out a prime factorization, meaning that we're going to have to make a factor tree, and then we will be able to circle our matches. Let's start with 72. Logan, what could I break 72 into? Yeah, come up with two numbers that multiply to 72, other than 1 and 72. Who figured it out? What can we divide it into? Deshaun? Beautiful. 2 and 36. 2 is prime, but 36 is not. Deja, what could we divide 36 into? $18 and 2. Okay, not the only pair, but it's one that works. 2 is still prime, but 18 is not. Natalie, what could I break 18 into? 2 and 9. 2 is still prime, but 9 is not. Nevaeh, what could I break 9 into? 3 and 3. Okay, so my prime factorization for 72 is 2 times 2 times 2 times 3 times 3, but it's not just a 72. What else does it have with it? An x and a y. So on the end, I'm going to put an x and a y. Questions about that prime factorization before we move on to 120 x squared z? Keon.
What about x squared?
We haven't gotten there yet. Jaquan?
How are we doing it? All right, put 2 cubed and 3 squared.
So if we're finding a GCF, I would not recommend condensing them. You can, but if we're looking for matches, it's easier if we see it all written out. Okay? All right, let's get rid of the 72 so we can work on the 120. We break down 120. Delaney, what's something I could split 120 into? 10 times? What would pair with the 10, Delaney? Okay. Now, these can both be broken down. We'll start with the 10. Kelby, what can I break the 10 into? 2 and 5. Good. Now, those are both prime, so we can jump back over to the 12. Jakeem, what can I break the 12 into? 2 and a 6. All right, then we've got to break down that 6 still. Jaquan, what is it going to be? 2 and a 3. So our prime factorization for 120 is 2 times 2 times 2 times 3 times 5. So make sure you use up all of your prime numbers here. Don't use any numbers that you broke down. Now we're on to that x squared z part. If I've got an x squared, how many x's should I write? 2 of them. X squared means I've got x times x. How many z's should I write? 1. Now I'm ready to look for my pairs. Lexi, what's one pair that I've got? I got a pair of 2's. So I'll write down a 2 from that pair. Ryan, what else do I have a pair of? 2 more 2's. So I'll write down another one. Connie, what else? 2 more 2's. Got another pair there. Okay. Kyan, what else? Got a pair of 3's. Keon, anything else I got a pair of? X's. So I write down an X. Do we have any more pairs? No. If we are out of pairs, then we are ready to figure out what this equals to know our GCF. 2 times 2 times 2 times 3. $24. And then the X just stays on the end. So that means our GCF of those two terms is 24x. All right, I want you to try number 8 on your own for a minute, and then we'll go over it together. Anyone want to volunteer to tell me their prime factorization for 21x cubed y? Good. So for the 21, we've got a 3 and a 7. Anyone else get the rest of that goes with it? Keon?
3 x's and 1 y.
Okay, x times x times x times a y. X cubed means we've got 3 x's. Until we get more comfortable with this, I would go ahead and write it all out. Any volunteers to tell me what we got for the 6x to the 6y cubed? Tariana? Okay, we got a 2 times a 3 for the 6. Ryan, you want to pick up the last part of it?
6 x's
Okay.
and 3 y's.
6 x's and 3 y's. A lot going on back there. All right. Questions about how we made these lists? Prime factorization. Now we have to figure out what our matches are. Danielle, what's something that matches? We got a match of x's, sure. So that can come down here for our list. May, what else do we have that matches? We got another x that matches up. Okay, Houston, what else? Those 3's. So I wanted to make sure we understood that even though they don't line up, that does not matter. They don't have to line up top to bottom. I could write this any way I wanted to. If there's a match from both lists, we're going to write it down. Jamal Dixon, what else matches?
Another x.
We got another x that matches. Good. Jerry L, anything else that matches?
Y.
We got a y that matches. Anything else we see that matches up? No, the only thing left on the top is a 7, and there is not a 7 on the bottom. So if I were to multiply all that back together, my GCF would be 3x to the 3rd y. There's my GCF. Questions, concerns? Okay. We will continue on. Maybe. There it is. All right. So this one we are now having to simplify, which means we would cancel out our matches. So when we're looking for a GCF, we're trying to pick them out to multiply them together. If we are simplifying, we're trying to cancel them out. So we could either write this out all expanded, or we can use our exponent rules to help us out. I'm going to recommend using your exponent rules, but if we need to expand it out and cancel, that's also okay. All right, in the numerator, let's go ahead and expand this one. We'll try to use our exponent rules on the next one. In our numerator, we are going to break down negative 24. Now, I would kind of just leave the negative sign off and treat it almost like there's a -1 out in the front. And then we'll just multiply that -1 to whatever we get when we break down 24. It's not the only way to think about it. It's just a good way to think about it. Otherwise, if you end up with negatives in your factor tree, it's a little confusing. So if we break down 24, Tariana, what could I break it into? 2 and 12. 2 is prime, but 12 is not. Deshaun, what could I break 12 into? 2 and 6. Jamaro, what does 6 break into? 2 and 3. So we can put all that in our numerator. 2 times 2 times 2 times 3. We've got that -1 out in the front because our 24 was negative. How many x's am I going to have? 3 of them. How many y's? 5 of them. And how many z's? 1 of them. Now, this is not going to be the most efficient way of doing this for the rest of our lives, but we'll do it this way this time. Next, we've got to break down that 36. What can I break 36 into?
2
What? 2 and 18. 18 breaks into? 9 breaks into? Okay. We go to put that up there. 2 times 2 times 3 times 3. How many x's? 1. How many y's? 2. How many z's? 1, 2, 3, 4. Now we are going to cross off our matches. What's something I could cross off? Pair of 2s. What else? More 2s. What else? Those 3s can cross off. What else? A pair of x's goes. Anything else? A pair of y's. Another pair of y's. A pair of z's. So when we go to rewrite this, anything that's left, we're going to multiply back together. So I'm going to multiply this -1 to the 2 that was left up there, and that gives me -2. How many x's are left? 2 of them, so that's x to the second power. How many y's? 3, so that's y to the third power. How many z's are left in the top? There aren't any. We crossed off the only one that was in the top. So then we move to the denominator. As far as numbers go, what's left? 3. How many x's? None. How many y's? None. How many z's? 3 of them. Notice that in the very beginning, the original problem, for the x's, where was the bigger exponent, the top or the bottom? Top. What about the y's? Top. Notice how our x and our y both stayed in the top in the end. Bigger exponents, it's where it ended up. What about for the z's? The bigger exponent was in the bottom, and where did z end up? In the bottom. Okay, you can always kind of do that check at the very end to make sure that your answer is reasonable. All right. On number 11, we are trying to figure out what this last set of parentheses would have to be if our original problem was 48 p to the 5th q to the 4th. Now, the easy way to do this is to multiply these things together and then divide the other side by it. So what is 2 times 4 going to be? 8. 2 times 4 gives us 8. What is 48 divided by 8? 6. So I know that I'm going to have a 6 back there. Does that make sense? Okay, what about p times p? That would give me p squared. So I'm going to take p to the 5th divided by p squared, and what do I get? P to the 3rd. So I know what p to the 3rd is part of my parentheses back there. Finally, I'm going to take the q squared times the q, and that is going to give me q to the 3rd. So I take my q to the 4th divided by q to the 3rd, and I get q, or q to the 1st. That's the last part of it. Just do it one piece at a time. The side that's together, multiply them together. Divide what's on the other side by that. Does that make sense? So even though I wrote it in 3 colors, that's my answer. Our homework assignment is on page 192, 11 through 25,
Oh my God.
31 through 43, the odds, and also 47 through 49.